Now I want to talk about sufficient statistics. So suppose on index set data, taking values 1, 2, and so on up to n, and the family of probability mass functions parameterized by data. And basically you have distribution f1x, f2x, fnx, and so on. And then basically we let x be a sample from a particular distribution belongs to this family. And we let t be a function of the sample. Okay, so it is a statistic, basically a decision variable for inference of data. Okay, so in this case, we can say that there's a Markov chain from data to x to t. And in this case, then mutual information between data and x, mutual information between data and t, there is a data processing inequality. Okay, and when the equality is achieved, we call t the sufficient statistic, a sufficient statistic for inference on data. Basically, it means that the decision variable t does not lose any information. Okay, so it has as much information as x can have about data. Okay, so that's what the notion of sufficient statistics is. And let's consider an example. So in this example, we want to consider a sequence of coin tosses. Okay, and this sequence of coin tosses is Bernoulli random variables, so x1, x2, and so on, and this is independent, identically distributed with one random variable, and each random variable taking value from this set. So it is either 0 or 1, so binary, so it is a Bernoulli random variable, and with the unknown parameter data. So basically the probability that xi is equal to 1 is data. So data is a number between 0 and 1. Okay, and then we want to show that given n, the number of ones in n trials is a sufficient statistic for inferring data, what data is. So that t, the number of ones in n trials, is basically sum of all xi's. That is basically number of ones in this sequence of coin tosses. So coin tosses here means that 1 is top and 0 means bottom. So basically how many number of tops has appeared in n trials. That's the sufficient statistics t, and this t is a sufficient statistic for inferring this probability. Okay. Here is an example that the setting is exactly the same as what I have said in the lecture note. So consider a sequence of coin tosses, independent and identically distributed. Shorthand notation is IID. With this setting, with an unknown parameter data, which is a probability of a coin toss to be had. So this is the setting, the same as the lecture note. And then the statement is that given the total number n of coin tosses, the number of ones in total n tosses is a sufficient statistic for inference on probability that x is equal to 1. Okay, so is this a statement true or false? That's the, instead of yes, but true or false. We have to evaluate this statement and show if it is true. Okay, so here is the sketch of proof. We let t to be defined as this variable. So sum of xi's. So since xi is either 1 or 0, this means t means how many number of ones in n trials. To show that t is a sufficient statistic for data, we need to show that mutual information between data and x should be equal to mutual information between data and t. Okay. It can be also proven by showing that we have a Markov chain from data to t to x. If this is shown, then we have a t, which is a sufficient statistic. And this relation from data to t to x is a Markov chain, can be proven by showing the following holds, showing that the following holds. Okay, I think showing that the following holds. So this one is nothing but for each x, t, and c dummy variables, x and t and c, Markov property holds. So basically, given t and data, x depends only on t. Okay, we have to show. So that's the sketch of a proof that we have to show. So in this case, there are two parts. First, I want to show that data to x to t is a Markov chain. Okay, so to show this, we have to show Markov property this way. So future given past and present should be equal to probability of future given present. We have to show that. That's first thing that we want to do. And the second thing that we want to do is that in order to show that t is a sufficient statistic, we have to show Markov chain relation from data to t to x as well. So this one, to show this, we have to show this holds. So probability of x given t and data should be equal to probability of x given t. So the first part, let's show. So we consider, again, we have to show this. So we consider this part. See, so probability t is equal to dummy variable t and a random variable x to be equal to dummy variable x. And then using total probability theorem here, the first line is total probability theorem, but we have a continuous random variable data, so we have to consider integration. But as I told you, in the probability of a primer, you can treat it as a summation, okay? So all you have to be careful is that this random variable should be, you have to consider an interval. okay, basically interval, okay, rather than a particular point. So that's all you have to be careful, and the rest of them is just same as summation, discrete random variable. So you can treat it as a discrete random variable by writing in this form. So we consider every possible data what dummy variable C. So basically this data takes a value in this interval, so you can just treat that this is data equal to C, okay? Treating like a discrete random variable. So that's the joint distribution T and data given X, okay? Now we apply conditioning. So you condition on data, so you have to have this term, okay, probability of data given X, okay, and we can now consider this part, okay, and that part is nothing but that part is nothing but the X that you have the probability that T is equal to T, then basically sum of all these X should be equal to T, okay? When it is not equal to, when T is not equal to small t, then basically such probability is equal to 0, okay? So all that has left is this, and then basically rest of them stays the same, and this part is equal to this. So I haven't done anything, just the playing with the notation, and then bring this to this part right here, and then since this is a conditional distribution, the integration should be 1, and all I have to do now is to evaluate this one. As I told you, this one is dependent on the random variable x. Okay, so when the sum of x's is equal to t, this probability is equal to 1. So if t is equal to sum of these xi's, then this is trivially 1. If it is not equal to t, the sum of these xi's, then the probability is 0. So this probability here is equal to t given data and x. As you can see, this conditional distribution is equal to the t given data and x. So there is a Markov chain from data to x to t. Okay, so one part has been proved. So this part